This tutorial is all about the effect of a change of concentration on the rate of reaction. And if we want to change the concentration of a substance, then what we need to do is to add more water to it. Like this orange squash, we'll add more water to it to make it more dilute. So dilute is the opposite of concentrated. At foundation level, we need to describe and explain the effect of changing the concentration on the rate of the chemical reaction. In many chemical reactions, we can follow the rate of the reaction throughout the experiment by taking, for example, the volume of a gas collected at various times throughout the reaction. But occasionally we come across a chemical reaction where we can't do this. One example is the disappearing cross experiment, and that's a reaction between hydrochloric acid and sodium thiosulfate solution. This produces a precipitate of sulfur which gradually gets more and more clouded until it obscures the cross. So for this experiment we take the time taken for the experiment to obscure the cross, which is a fixed point for each type of reaction that we do. And in this case what we'll look at is how the time taken for the reaction varies when we change the concentration of the sodium thiosulfate solution by adding more water and less thio as a mixture. If we were to perform this experiment, we might get a set of results like these, where as the concentration of the sodium thiosulfate increases, as we have more thio and less water, we end up with a lower time taken for the reaction. In other words, the reaction is faster. Plotting this data would give us a graph something like this, with the concentration increasing along the bottom and the time taken to obscure the cross up the side. And this would show us the curve of best fit. And as we can see on this graph, if, for example, we double the concentration from 0.2 to 0.4, we halve the time taken for the reaction to take place. Therefore, we're doubling the rate. Looking at another set of data, if we double the concentration from 0.4 to 0.8, we're halving the time taken from 100 seconds to 50 seconds. In other words, we're doubling the rate. So it seems that if we double the concentration, we double the rate of reaction. We can think of this chemical reaction between the thio and the hydrochloric acid as being between particles of each of these substances. Now these particles will be moving quickly and will collide with each other randomly. However, if we have a more concentrated thio solution, then the thio particles will be more crowded in the same volume, and that will lead to more frequent collisions with the acid particles and therefore a faster reaction. Let's look at another example of a chemical reaction, for example between solid magnesium ribbon, which is shown as these black particles in regular positions because they're a solid, and hydrochloric acid. In a dilute solution of hydrochloric acid, there are few particles in a given volume, and therefore there are not very frequent collisions between the acid particles and the metal. However, if we were to double the concentration of the acid, then we double the crowdedness of those acid particles around the magnesium, and we double the frequency of the collisions, and that will double the rate of reaction. Here's an example exam question. Rob and Catherine investigate the reaction between sodium thiosulfate and hydrochloric acid. A yellow solid is made during the reaction. Look at the diagram, it shows the apparatus they use. So they're putting it in a beaker, in this case, on top of a piece of paper with a cross on it, and the beaker contains the sodium thiosulfate, or thio solution, and hydrochloric acid. Rob and Catherine look down at the cross, the yellow solid is made and liquid in the beaker becomes more cloudy. After a time they can't see the cross, and Rob and Catherine measure this reaction time. They do the experiment 4 times using different concentrations of sodium thiosulfate solution labelled A, B, C and D, and they do all the experiments at the same temperature, 20 degrees, so all the particles, I presume, are going to be moving at the same speed. We're asked to look at the results, and the different concentrations of sodium thiosulfate gave us different reaction times. Now, which concentration of sodium thiosulfate gave the fastest reaction? Well, the fastest reaction will be the one which is over in the quickest time, which is here at 41 seconds, and therefore the answer to that part is solution A. Now, which is the least concentrated solution of the sodium thiosulfate? That will give us the slowest reaction, which will be the longest time, and the longest time is for C, 135, so the answer to this one is C. You're also expected to be able to understand data not just in tables, but also in graphs and in written form, and be able to identify which is the faster reaction by looking at this data, for example, by the shape of a graph. Now we know from a graph that the steeper the curve is, the faster the reaction is, because it means that there's being more product made in the same amount of time. So when we look at these two graphs, we can see that in the first 20 seconds, for example, then this 1 mole per cubic decimeter solution of hydrochloric acid is producing only around about 20 cubic centimeters, whereas this 2 mole per cubic decimeter solution is producing around about 35-40 cubic centimeters. So that one must be a much faster reaction. So we can see from these graphs that the more concentrated the solution is, the faster the reaction is. Now the reaction is complete when no more product is made, in other words when the graph becomes level. We can see that this graph here becomes level after around about 120 seconds. But we can also see that in this case there is less product made, less hydrogen made, than in the case with the hydrochloric acid. This is because the hydrochloric acid is the limiting reactant. So if we are using a more concentrated hydrochloric acid solution, then we will get more product made, and therefore the higher concentration graph will not only be more steep, but also will level out at a much higher level. Summarizing that, if the concentration of a reactant is doubled and it's the limiting reactant, in other words the other one there's more than enough of, or it's in excess, then the mass or the volume of the product will also be doubled. And that's shown here more clearly. For example, this is a reaction between hydrochloric acid and marble chips, which produce carbon dioxide gas. Solution A is a more concentrated solution at 200 grams per cubic decimeter of acid, whereas B is only 100 grams per cubic decimeter of acid, and they've got more than enough marble chips to react with. That means that the amount or volume of the carbon dioxide which is produced on the left hand side is going to be related to the concentration of the two acids. Now they've got the same volume, but A has got double the concentration, then A has got double the number of particles of the hydrochloric acid, double the number that can react with the marble chips, and therefore produce double the volume of the gas. So we can see that this one is producing 40 cubic centimeters of gas, whereas B is only producing 20 cubic centimeters of gas. The other difference, of course, between the graphs is that the steepness of the curve varies, because A is a steeper curve, it's a faster reaction because A is a more concentrated acid, and therefore with the more crowded particles has more frequent collisions, whereas B is more dilute and has a slower reaction.